She'll talk about harnessing residential loads for demand response. Okay.
Thanks, Sean. And thanks for having me here today. So my PhD is in mechanical engineering, and now I'm sort of becoming an electrical engineer. And in this talk, I'm trying to also present my knowledge of economics. But since I'm not an economist, I actually teamed up with a PhD student at ETH, Tobias Haring, who has a master's in economics, but is studying electrical engineering for his PhD. So he's not a real economist either, maybe. But at least we were able to discuss some of the engineering and economic challenges when implementing residential demand response programs. So this talk is sort of diving a little lower than the last talk and focusing really on residential loads and what kind of demand response programs you would need to get the customers on board and what kind of signals they would see to be able to respond to demand response. So, and also my talk has a little in common with one of the talks yesterday, John's talk, pitting sort of the engineer versus the economist. So Tobias and I sat down several times over the last couple of weeks and just said, so how do you see this problem? Or what is demand response? How do you define it? How do you think we should deploy it in systems? And again, this is all focused on residential loads, which have different requirements than commercial buildings and industrial loads, which might not need the same kind of signaling and contracts that a large customer would need. So what exactly is demand response? So could it be a mechanism to improve electricity markets? Maybe that's more the economist perspective. Or is it a new control variable that can enhance power system reliability and security? And based on your answer to that question, or your bias towards one definition or the other, you might have a preference for dynamic electricity prices or direct load control. And so this is sort of an ongoing argument in this field. Do we engage with the residential customer by sending them prices, or do we have them sign contracts and do direct load control? And so the idea for this specific work actually came from a meeting at Los Alamos National Lab, which Sean was at and I was at back in May. Several people here were at, actually, where we had a debate about this, and there were people who had very strong opinions in one direction or the other. So the goal of the paper that we wrote was to analyze the engineers and economists' perspectives side by side to really understand when you would design a program one way versus another based on the program's objectives. But the larger goal here, because I'm not going to really answer that question directly, I'm just going to show you the map of sort of what we came up with, was really just to bring the arguments together so that we can understand each other and reach some kind of consensus to move forward on these programs. So these are the real engineers and economists behind this work. I just wanted to show you Tobias, and also Jorn Andersen is my postdoc advisor who is involved in this project. So the outline of my talk is as follows. First, I'm just going to go back through the debate a little, but we discussed this yesterday, so I'll go through it quickly. And then talk about options for harnessing residential loads for demand response. And then I'm going to look at 3 specific detailed examples of demand response implementations for residential loads, and then compare the engineers' arguments for and against each design against the economist perspective for each, bringing up the points where they actually do agree, because there actually is a lot of agreement, but different word choice, like we make the cases differently and choose different words, but we actually have a lot of agreement, and then areas where we disagree. And then finally sort of summarize and make some conclusions, which are more questions for future research than conclusions, but you'll see that. Okay, so the big debate, how should we engage residential loads? Should they see prices? Should they be controlled directly, or direct market participation? So these 3 topics actually map very closely to what David had just presented earlier. Direct load control I'm sort of using as the reliability product that he mentioned. And market participation is when they actually participate in the market, so it's the economic demand response. And then dynamic prices is that other category where you don't have a guaranteed response. And does the answer to that first question change based on what kind of service demand response is provided? And the service of the demand response is related to the time scale of the demand response. So we know that there's lots of different services that can be provided, and then the time scale can vary from microseconds, so they can have instantaneous response to some issue in the system, like a frequency drop, all the way up to hours and maybe even more than hours. So should you send prices if you sort of need a slow response, or direct load control if you need a fast response? I mean, there's a lot of debate about a lot of these questions. And then the issue, of course, is that a lot of these goals come from different fields. So there's technical goals, economic goals, and environmental goals. Some of them are the same between, some of them compete against each other. So based on which perspective we come from, we might be thinking of one time scale versus another, and that also affects how we perceive what kind of signals we should send to the loads. So since I'm an engineer, I'm usually thinking technical goals. I'm thinking about reliability and security, fast timescale demand response, and for me, direct load control. But we'll leave that open to debate later, too. So just briefly to summarize the views, so the engineer's view is that the power, so this is the problem in both cases, so that the power system is hard to accurately model. It's very complex. Because we don't have good models of it, we need feedback control. The system is huge, nonlinear, uncoordinated. There's different control systems and different balancing areas that sort of compete against each other sometimes. It's really hard to nail down that problem because you have people who aren't talking and exchanging the right information to make the right global decisions for the system. And of course, there's all these stochastic things like loads, generation, contingencies, et cetera. So then we see DR is this new control knob. But even though it's a control knob, and from our perspective, it's sort of a technical thing we can use, using it is still an economic decision. So I just wanted to clarify this, because yesterday, I think when we were pitting the two side by side, we were saying that engineers don't always consider the economic implications of their control decisions. But usually, we can assign costs to control decisions. So we would only choose DR if it was cheaper in some way than the other alternatives. And engineers are always trying to decide how to turn technical costs into dollar costs to make these decisions properly. And of course, from the economist point of view, we talked about this a lot yesterday, so I won't run through this all. But the market has a number of market failures, and DR can alleviate many of these market failures. And just to bring up one specific example, we talked a lot about how reliable electricity is a public good. And there's been studies all the way back, 25 years ago, that looked at this issue of how to make reliable electricity not a public good anymore, and actually give different levels of service to different customers based on their desires. So this demand subscription service with Chow and Shmuel Oren at UC Berkeley, and they proposed this long ago. Of course, it wasn't ever implemented or anything like that, but people have been talking about this issue for a long time, how DR can help with these issues. And so for this talk, why am I focusing on residential loads and ignoring the commercial and industrial loads, especially because those loads are big, and so we think we should go for the big loads first usually because we get more demand response. But small loads actually can have a number of advantages over large loads, or we think that they can. For instance, they can be very reliable in aggregate, which means that it's very likely that a large portion of them will be available because you have so many of them. Whereas if you have a smaller number of large loads, if one goes down, it might really affect your demand response potential. In addition, they have small loads have simple dynamics and controllers. So my previous work actually looked at commercial buildings and how to control them for demand response and how to make them do fast demand response. But large commercial buildings have these very complex control systems with cascading controls, and it's really hard to get the building to do something very specific down the line because you have one interaction that causes some other effect, and you can actually have energy rebounds you didn't even expect in the system. But these small loads are very simple. They're usually on-off, or there's just sort of like a rheostat, and so you can tell them what to do externally, and they do it more consistently than these large buildings. And so in our experience, because they're simpler, they're easier to control in aggregate. They're also spatially distributed, so they can provide local services, which we haven't been talking about too much here, but issues like if you have a lot of PV integration on a distribution feeder, and you need to make sure that the PV integration doesn't cause huge spikes in generation, which causes voltage problems, you can use demand response to solve some of these problems. And so they can be used for local and global services at the same time. And also, they exhibit continuous response to control signals in aggregate. So if you have 1,000 small loads, you can actually have them follow very smooth signals. With large buildings, it's sometimes harder to do that. It's not necessarily a technical issue going forward, but right now with the control systems for large buildings, it's hard to have them follow continuous control signals. They're really good at doing step responses, like you change a set point and then they decrease their consumption. And you can see that in the data when you collect data from these buildings. But if you're trying to have them follow a regulation signal, sometimes it's harder to see. But there's some really great work going on here too by Prabir and Sean, where they're actually looking at this issue of how to make them more continuous, large buildings. So that's not a technical issue going forward. And then another point is just that we do have residential demand response programs, and David mentioned this in his talk, but a lot of them are pilot programs, and so there's still a lot of debate right now about how to implement these programs properly. And then two more issues. One is that residential loads actually have a huge resource potential. And when I'm talking about residential loads here, I'm usually talking about thermal loads because they have thermal storage. And so when you have thermal storage, you can think of the loads sort of like a battery. And you can't just characterize them with their power capacity. You have to also think of their energy capacity because a battery has a limited amount of energy. So what I'm showing you here is a study that we did at Berkeley where we characterized the technical potential of air conditioners, heat pumps, water heaters, and refrigerators in California. So if you were to get all of those loads together and control them in a non-disruptive way so that the consumer wouldn't notice the control by cycling them on and off relatively high frequency, so making them switch on and off faster than they would otherwise, you can think of that resource like a large battery. And you can calculate an energy capacity and a power capacity. And how you read these plots is that you think of this like a load duration curve, but instead it's a resource duration curve. So if I stack up all the hours in the year from the highest hour capacity to the lowest, I get something like this. So for instance, refrigerators are always available in a system. So over all the hours in the year, you have the same resource capacity. But an air conditioner is only available when it's really hot outside. So an air conditioner is available a lot when it's hot and not at all when it's cold. So the capacity for the air conditioner decreases throughout when you stack up the hours like this. So you can look at an energy capacity and a power capacity, so how much energy is there and how much instantaneous power you can get by switching them on or off. And that characterizes the battery of all these loads in California. And what you can see here is that it's actually quite large. And of course, this is a technical potential, not an economic potential. So you probably, you can't get all of this. But you're looking at 8 to 10 gigawatt hours of energy storage from these loads by keeping them within the comfort band of a consumer, which means we're not changing anything about the consumer's preferences for cooling or heating. All right, and then the issue is the money. So we have a large resource potential. How much money could they make by participating in markets? And so we also did an analysis where we took this data and computed how much money could these sorts of loads get by participating in regulation. And we looked at load following, arbitrage, and other potentials. Regulation is the highest revenue potential because the markets pay the most. And we're looking at ranges here for air conditioning and heat pumps because, again, it matters where you are. So if you're in California, you can make $10 per year per air conditioner to participate, or sorry, if you're in Berkeley, you can make $10 per year per air conditioner to participate in regulation. Not very much because in Berkeley, my air conditioner is on 5 days a year. But if you're in the desert, it can be much higher, 80, and it actually can increase. This isn't the total upper bound. So it's more like 100. Water heaters and refrigerators, it doesn't depend on your temperature because they're always on, so that's why this is fixed. So is this compelling? We're not sure. It still seems pretty low, but these prices are based on past data, past markets. Markets are changing, and this is sort of just gives you order of magnitude ideas that there might be market cases for this in the future. And depending on how things evolve and how market prices evolve, these could change and go up or down. So we still don't know if there's like a really strong market case for this, but we're exploring this issue anyway. So when designing a residential demand response program, there's many different decisions to make. First, you have to decide what's the objective of the demand response scheme. And based on your objective, for instance, if you choose ancillary services provision or some specific objective, you might help certain players in the system and harm others. So you might have the transmission system being benefited and the distribution system not be. So usually these decisions about what's the objective of the program aren't like a global benefit to the system. But they can be, but they're not always. And there's also decisions to make about which power system actors are involved. Who's offering the program? Are there aggregators involved? Is it a utility who's involved? Or is there direct interaction with the ISO? And then who makes the decisions in real time? And just to briefly go through the different actors, I think everyone here knows about the US power system market and design. But we did this analysis also for the European system, which is much more complicated because the European system, or the continental Europe, separates the reliability obligations from the market operations. So there's a market operator and retailers that interact with customers, but they don't provide any sort of reliability in the system. Instead, there's a distribution system operator, transmission system operator providing these services. So the markets happen without any notion of the actual grid and the physical constraints of the grid. So the transactions are settled, and then the transmission system operator has to procure ancillary services separately and run the optimal power flow and figure out if everything's going to work. So the market isn't settled based on an optimal power flow. So I think eventually they'll come around to this, but there's a lot of issues that are caused by this issue. And then there's these virtual entities called balancing groups that are supposed to help the transmission system operator by declaring what the power consumption is going to be in the future. So the balance group will aggregate generators and loads, some combination, and by the way, some of the generators are actually under the distribution system operator instead of the transmission, which is also confusing. But they'll aggregate these and then have to follow the schedule that they said that they were going to follow. And then if they deviate, they get penalized. And so, but these are just virtual entities. They're not physically connected, but they're supposed to help with reliability for the grid. So if you do a demand response program in Europe, you can imagine you could do it through the balance group, the distribution system operator, retailer, or TSO, depending on what the objective of your problem was. So it makes it very complicated. Okay, so back to so many decisions to make. So the other decisions are, so then after you've chosen the actors, what signals do you pass back and forth? Prices, direct control signals, and so forth. And what's the time scale of these signals? And of course, the time scale goes back to this first question of what are you trying to do? And then finally, how is demand response rewarded? And so that last question is the way we usually classify demand response programs. There's two primary types of programs according to a lot of different, in the literature basically. And so the one option is the time differentiated electricity rates and then incentive programs. I think David's broke it out to 1, 2, and 3. What I'm going to do is go through 3 examples. So dynamic electricity prices is one example, and look at the engineering and economic implications of that. Direct load control, and then the last one, direct participation in energy markets. And then in terms of the state of art, so a lot of this has been implemented in pilot programs, and people have mentioned that in Florida there's actually some implementations here that use pool pumps and air conditioners and things like that for cycling. And here are some other examples. Most of my experience is from California, and I'm starting to learn the Swiss system a little, but there's been implementations of critical peak pricing, remote shutoff programs, and also these really interesting spinning reserve demonstration projects in California, where they use the loads to provide spinning reserve, so ancillary services, but they did it through direct load control via an aggregator. So the aggregator sent direct load control signals, and then the aggregator participated in the market. And then there's been Pacific Northwest National Lab has done pilot studies with direct participation in energy markets. And then this is sort of an interesting one that in Switzerland for the last 20 or 30 years, they've had these programs that are required, and customers don't get compensated for participating at all. But if you buy a water heater, you have remote shutoff capabilities through power line communications, and they call it ripple control. So if there's a problem in the system, they'll send these signals via the power lines to shut off water heaters. And they also use it to shut them off a lot during the day so that you're only using your water heater at night. And I've also heard in France there's similar programs with heaters. So there's a different way of thinking about it a little bit in Europe. In a lot of cases, they don't perceive that there should be compensation to the customer for emergency actions like this. So it's something for us to think about here. Okay, so for example 1, so I'm just going to run through each of these examples. So price signals, we talked a lot about this yesterday. I'm just going to bring up a couple additional issues. But in this example, what we were analyzing was if we have some kind of entity, and we don't have to specify specifically what kind, sending prices to the customer and the customer deciding what to do with those prices and controlling their load. And we assume that the prices are formed based on the wholesale markets, but there's no bidding. So as a customer, I don't reveal my preference in advance. The market has to look based on past information and forecasts. So this is the issue that I think John was talking about with instability issues a lot. And if we start thinking about how often prices could be updated hourly versus instantaneously, we get to different conclusions about how well the system would work. And there's also this really interesting point of, do you send every customer the same price at every time, or do you do it based on locational marginal prices? And what are the implications for the customer if it's locational? So Tobias helped me with a lot of this, like thinking as an economist, what would an economist think of this problem? And the pros of this perspective is that the pros of this setup is that the customer has the full knowledge of what they want, so they can do the best optimization. They can optimize their current consumption, but also their investments. And also they like it because there's privacy. I get signals, I don't send any information out. There's some observation from the system of what the system does based on the prices, but my own preferences aren't revealed directly. And then the customer also has autonomy in real time to make decisions. So if they decide that they really need to watch a football game, then they keep the TV on. And that's, some people perceive that as very important. And the cons, of course, are that there's financial risk. And so in order to address risk, you have to make markets more complete and offer hedging strategies and things like this to consumers, so maybe they're not directly facing the prices in real time. There's also really high transaction costs if you do fast demand response, because there's a lot of interaction with the customer. So you're sending prices updated, and then the markets are closing, and then, so there's just a lot going on in real time. So the transaction costs can be high if you're trying to do really fast demand response via this mechanism. And then, like I mentioned before, with locational prices, there's these issues of fairness. So I was talking to some people at Pacific Gas and Electric Company in California, and they were saying that if they actually had locational prices for the retail customers, the prices in San Francisco would be about 4 times what they would be in Berkeley, which is right across the bay, and this is all because of congestion. And so customers would see such different prices that everyone who had a plug-in electric vehicle in San Francisco would drive it over to Berkeley and charge it every night. It would create all these really strange incentives. Right. Yeah. Right. And so there's these questions of, will the customers perceive will the fairness effects then affect their perception of how well the program is operating and things like that. So it's just something to take into consideration. But if we do want the optimal sort of system, then we would have locational prices, because locational prices represent congestion, and that's the thing that we're trying to price around a lot. So that's one issue. And then, as John mentioned yesterday, that people's preferences for electricity are not well behaved in the economic sense. So the outcomes of these markets aren't perfect based on the theory, because the theory has a lot of assumptions that don't hold in real life. And then, of course, the last issue, which we talked about a lot, volatility, instability, and so forth. I'm just going to leave that because we've heard about it. And then this is just a visualization of how when you have a dynamic market, you can lead to instability. So if you just look at a supply-demand curve like this, and you start somewhere on the curve where you're not at equilibrium, you're trying to converge to the equilibrium, so every point is a point in time. You can converge to it. You can converge to the equilibrium by spiraling in. You can actually deviate from it by spiraling out, and this just is a function of the angle of these lines. So it's a very easy way to visualize this problem. Or you could just hit a limit cycle. And so it's very easy to understand how these instabilities could occur if the market's not set up properly. And so from the engineer's perspective, why do I like this setup? Well, I like it because if I'm trying to do the modeling and optimization and control for the customer, it's an easier problem than for the aggregate, because I know their system, I can model it fairly well, I can control it fairly well. So this is actually very similar to the economist argument, right? But it's more from a modeling perspective than an economic perspective. Also, I like this one because there's no bidding involved. I don't need to, in advance, decide what my preferences are. I can just see the price and then decide what my preferences are and do something based on that. But I don't have to come up with a bid in advance, which might, for an individual customer, might be quite hard. And also, there's no baselines. So David mentioned this earlier, but baselines are very tricky. So if you don't have to measure your consumption versus something else, it just saves a lot of hassle in trying to figure out what you're reducing your consumption versus. But then there are many cons. So because the power system can't respond instantaneously to changes because there are physical constraints in the system. There's long ramp times, there's not that much storage. You could have situations where the prices don't induce the behavior you expect and you have system inadequacy. And then there's lots of technical issues like synchronization and rebound peaks. If they're receiving the same prices, they're doing the same thing, and then the system starts oscillating, which is a sort of a price instability problem too, but also a technical instability. And the way I view the system is sort of like a delayed system. The market closes, you see the price, it's active for a certain amount of time. As time progresses, that price is less and less relevant to when it was set. So the system is becoming more and more delayed, and as control engineers know, delays can cause instabilities. Okay, so just example 2. So direct load control. In this case, the customers enter contracts And I'm using the word direct load control very loosely. Traditionally, it's been used to say, I'm going to control your load to do something, usually to turn off when there's a system emergency. But here it just means any predefined contract to control a load in a predictable way. So customers enter contracts that can be centralized with an aggregator or with a coalition of other loads. So they're interacting with other loads and developing a contract to act in a predefined way. And then the actual signals they see could be set point changes, power trajectories, anything. Could even be prices, as long as the prices induce a predictable behavior that's pre-programmed in advance and based on the contract. So it doesn't matter what the signal is. Okay, so just very quickly to run down the economist perspective. Tobias liked this one a lot at first because of the low financial risk, the low transaction costs. It's easy to implement and simple for the customer. And I think we don't have really good values for simplicity in systems, and it would be great to include those in systems, because if this is the most simple to implement, then in some sense it could be more efficient if we could value the simplicity from an economic standpoint. But the cons, of course, are that the customer perceives they have no real-time autonomy. But you could build in some in the contract. So you could say that the customer can opt out X times a year. So there could be some built-in autonomy. Also, there could be privacy issues with two-way communications if you're doing direct load control. And then just implementing this might be hard. For instance, trying to get the customer to tell you what their true costs and benefits are so you can create the right contract. How do you elicit that from the customer? Because you need to do that in advance. And then compliance is hard. How do you check that they're doing what they said they're doing without excessive monitoring? But if you're looking at thousands of small loads providing these services, it's hard to monitor them. And so self-enforcing contracts are important. And I think that there could be a lot of really interesting academic work in this area, actually. Okay. So from the engineer's perspective, I, of course, like this because I have a lot of control over the system. I get predictable customer behavior. Based on the outcome of the contract, I know what's going to happen, so I can compute controllability, observability, and stability before I do anything and know what will happen with my system. If there's a chance of instability, I can change my controller, things like this. I might have some ability to fix problems in the system in advance. Another benefit is that there's aggregation and market bidding. So the aggregator is providing a service to the system level. And so the aggregator is aggregating all of its resources, so all the variability of each resource gets aggregated together, and then there's smoothing. So it's much easier for me to get a good bid that I can actually follow than for an individual customer to provide a bid. And then also benefits via coordination of diverse resources. So if you have a lot of resources and all they can do is switch on and off, they individually can't do very much. But if you aggregate them together and they can provide smooth-looking signals, then you can actually get more than the sum of them in aggregate, basically. So you can use this aggregation to get more out of them than you would have individually, with them all making their own decisions individually. But the cons are, of course, that you might need baselines. But I say you can design programs that don't require baselines to be computed based on models and things like that. For instance, customers could buy their own baseline in advance, which is a concept that was proposed a long time ago. And Severin Bornstein at Berkeley has written about this a lot, about in advance contracting your baseline and then having deviations from a baseline so that you're accountable to a baseline. So it's not like this issue of after the fact trying to compute what they would have done. So there are ways around this baseline issue in this case. And also, you need to do aggregated modeling, control, and optimization. And if you're controlling, so I list this as a con, but this is my research area. So in this case, it's a hard problem of figuring out how to model these loads well enough in aggregate, but make the model simple enough that you can do something with it. So either your model is incredibly computationally complex and you can't solve it, or you have to simplify it and it's not optimal anymore. But let me show you an example of this. So thermostatically controlled loads is a specific topic I work on. So air conditioners, water heaters, everything from the plot I showed you before. And the cool thing about these is that they have hysteretic on-off controllers. So they operate within a deadband. And so they have a temperature set point here, but they operate plus or minus that set point. And in this deadband, we can think of them as storing thermal energy, this concept we talked about earlier with commercial buildings. So just to make it really clear, if we're doing non-disruptive control with them, actually, first, the uncontrolled case. How do they operate? So they're off for some period of time. And then as the temperature is increasing, so I'm imagining this is like an air conditioner. The temperature is increasing. It hits the upper edge of the deadband. It switches on. It consumes power, cools it back down, and brings it down. But if I want to do non-disruptive control with these air conditioners, I can say, allow them to do what they would have done anyways, and then all of a sudden I need to increase the power of my system because I have a regulation signal that says increase power. So they get to this point, they're still within the dead band, and I switch them on. And then I let them do something, and then maybe I have another command, and I need to switch them off. And so for an individual load, they all look like this, on and off, on and off. But in aggregate, you can get a very smooth signal. Okay, so these issues of modeling and control, and then addressing the issues of the economists, for instance, like the privacy concerns and things, we can use engineering tools to do some of this. So here, this is an example of looking at how you would minimize communication costs, which is more of an which is both an economic and an engineering issue, and then privacy concerns to the customer. So if you take a lot of different loads on a distribution bus, and then you want them to follow some kind of market signal, and this looks like a load following market signal. I have some central controller. I want to broadcast control to the loads and have them follow some trajectory like this. And they probably can't follow it perfectly, but they can do a good enough job to participate in the market, so it would look like this. So there's different options for how I could communicate with them. In the most extreme case, if I wanted to solve the problem perfectly, basically, I could have offline and real-time information from the loads. So in real time, they're all transmitting to me as a central controller, as an aggregator, say, their state in real time, their temperature, whether they're on or off, and then I can make a really good decision about how to control them and what kind of control signal to send out to all of them. So what I need to do this is a dynamical system model. And then I need to build the model with offline information. So I have the model and I have offline information coming in. But in a more realistic case, maybe I can't talk to them all in real time. Or maybe I don't want to because the consumer perceives that if it's transmitting information to me in real time, it's giving away private information to the household. Or it's too expensive to talk to them all in real time. I mean, that's probably the most realistic case. So instead, I get some aggregate measurement of their power consumption at the distribution substation bus. But there's other loads here, and so the aggregate measurement looks messy. I mean, I don't have a good estimate anymore of what's going on. So I need a load state estimator to estimate what's actually happening at the loads. And so for this, I can use a Kalman filter, a particle filter. There's many different options for the state estimator. So this is a case now where I can still build a model. I have information about them, so I can build this model. But I can't talk to them in real time. I can send signals, but I can't get anything back. So this is helping solve the privacy issue. And then sort of in the worst cases, I don't even know much about them. So I signed them all up for the program, but I didn't get information about the specifics of their loads, so I can't build a model about them. So instead, I just have information from here in real time. So I'm sending them control signals, I'm seeing the output, and from that, I need to build my model and do joint parameter and state estimation. And there's many different tools for that. So this is really looking at the case where I'm not doing a lot of communication, and maybe it'll be okay for the customers because they know they're not sending me anything in real time. And there's not a lot of infrastructure in place either, so it's cheap. And so what does this look like? So if I have 1,000 air conditioners following a 5-minute market signal, they're trying to follow this signal here. So case 1 is where I know everything. I can do a really good job. But I'm still broadcasting control. There's a little bit of uncertainty in the system, so there's some wiggles around here. It's not perfect. This is 1 hour, a 1 hour 5-minute market signal from California. And case 2 is the case where I said they're not sending me any information in real time, but I still have a good model of the system. In case 3, I don't even have the model. So you can see there's this trade-off. The more information I have, the better I can do, but is this good enough to provide services to the system and actually respect the customer's preferences for privacy and for low-cost infrastructure? Yeah, we tried to talk to the generators and the ISOs to see if this is actually good enough compared to what the generators can do, and I think so, but they won't give us, it's all proprietary. Yeah. Yeah. So it's good enough, yeah. Yeah. Okay. So the key point here is engineers don't need to know everything. So when we're talking direct load control, we're not trying to get all the information from the system as much as possible. We can actually use all these really important control tools and techniques that we developed for other applications. Okay, so I think am I out of time already? Okay. 5 minutes. Okay, yeah, I can get through this. Okay, so. Okay, sounds good. Okay, this is my last example. This one's a little shorter. So, so the last one is sort of what we would love in terms of all prices and all preferences being revealed in a perfect world. So price quantity bidding by individual customers into markets. So all of their opinions and preferences are expressed in advance, and we have the market settle, and then we have outcomes, which then the loads would respond to in a predictable way because they've expressed their preferences already. So in this case, we assume that the bids of the loads are optimized against generator bids in an OPF, because that's the way to get the most optimal solution, including constraints in the system. And you could think of these timescales, days to instantaneous. If we could do it instantaneously, then we could actually solve all the problems in the system. We wouldn't need reserves or anything. We could just have these markets settling. And in this case, I'm not considering aggregation. So a lot of people say, well, why don't you aggregate the loads and then have them bid? But then that devolves back into example 1 or 2, because what I really care about is what the loads see, what's their interaction with the system. If they're aggregated, then they're getting something from their aggregator that's probably going to be direct control signal. It might be a price, or maybe they have internal markets. But in this case, I'm looking at their market participation directly in the system market. So Tobias loved this one, said it's economically efficient, there's full knowledge, there's privacy, and customer autonomy. There's also some issues, very similar to the ones we talked about before, financial risk to the customer, perceptions of fairness. But the big one, of course, is the transaction cost. It's probably not practical at all to implement this in a real system. You would have to have these markets very fast and so many players, and it would be impossible. So this is sort of what you would like to do but can't. And then from the engineer's perspective, again, it's no baseline, so that's great, individual modeling. The cons, of course, are that the individuals are making their bidding decisions again, and it's hard for them to do that. It's hard to set up that problem properly, to bid what you want your TV to consume in electricity for the next hour, especially with these flat screen TVs that don't consume a fixed amount of power. They vary over time. And then uncertain customer behavior could happen if they don't follow what they said they bid. But of course, the issue is that the OPF is non-tractable. It's already very, very hard to solve an OPF just with the generator market. And so with all these loads too, it would be a huge problem. So which is best? Dynamic pricing, I'm not going to give you the answer here, but dynamic pricing, direct control. There's lots of issues here, but the penetration level of demand response is important. A lot of the studies we've done that show that all of these work in various forms are with really small groups of loads, and so you're not going to encounter stability problems if you have a small pilot study. And so for small studies, just testing out these concepts, it's hard to say which one's best. We're not going to get answers yet, but the issue is going forward, if everyone's doing this, where will the issues start coming up? And then, of course, the answer to which is best is a function of the application, which is the time scale of demand response. So like I mentioned with this last issue, if you do the markets once a day and then set a day-ahead plan, but then have reserves and other things in real time, maybe that would work. But in real time, if you're doing markets to provide fast frequency services, then maybe this last one's totally infeasible. And then it comes back to these two, which with this one being a lot easier because of transaction costs and things and complexity. And then last, of course, is I'm going to throw in the customer preferences issue because that's pretty hard to see. But what will the customers be willing to accept? And I think there's a really so customers like to respond to prices, and they sort of know how to do it. But customers also don't really care about the details of when they consume energy. And so maybe customer preferences will be for simplicity, and then there'll be more here. OK, so my last slide. So overall, how much do we really disagree? I think that there's a lot of commonality in these arguments. We're just using different terminology. There's a lot of benefits in local decision making, but there's worries about volatility, instability, transaction costs, or complexity, depending on which way you look at the issue, and uncertainty and risk. But there's a lot of tools we have, and I showed you some from engineering that can help solve the economic concerns, and I'm sure there are some the other way around. And then for our perspective, we both, at the end of this exercise and listing all of these issues out, we both sort of agreed that if you really want to do fast, reliable demand response, we recommended some kind of contract-based direct load control, which might be via prices and things, but defined, like I said, where the prices have predetermined responses. But that the contracts are really important for providing the reliability. OK, that's it.
Thank you. Well, very good and interesting presentation, but my question obviously will follow my yesterday's comment, which means that you've presented the problem from the economist and the engineer perspective, but the most important element is missing. Where's the customer? How the hell do you know what the customer will accept? You may come up with the best possible strategy from the control engineering or from economic point of view, but if the customers don't accept it, it's completely useless. So I know it's not your fault, but I would encourage you to. That's Sean's fault, but I think it's more, if you could talk to Joran, and I'm sure he's aware of the problem, that I think social scientists should be involved in research programs like that, because
Sure.
that's the most important. If the customers don't accept it, it's basically
Absolutely.
you may not have done it as well because it's just.
So I think understanding this value of simplicity versus choice is really important. And I think that there's a role to be played by engineers who study human-centered design, and we're not bringing those people in either. I mean, they come more from an engineering perspective, but understanding how people act with engineering systems is really key here.